Hello everyone, my name is Abhinav Sharma and in today's video we will be discussing about quicksort. So a quicksort is highly efficient sorting algorithm based on the divide and conquer technique. It works by selecting a pivot element, partitioning the array into two subarrays around the pivot and recursively sorting the subarrays. Few characteristics to note about quicksort are that it is an in-place algorithm, which means that it does not require any extra storage to store the subarrays. It is not stable. Equal elements might not retain original order. It is recursive, that is, breaks down the problem into smaller subproblems, and it performs better on average cases when compared to bubble sort or insertion sort. Why do we prefer quicksort? First is because of its efficiency. The average time complexity of quicksort is big O and log n, and it is much faster than bubble sort and insertion sort for large data sets. It is an in-place sorting, which means it does not require any additional memory to store the subarrays, unlike in merge sort. It is widely used in practice. Many standard library implementation use quicksort or variations of it. It is fast on average case, it adapts well, and it is also useful in system level programming. Quicksort common uses: standard libraries, average case priority, large in memory datasets, and array and list sorting. And if we look into the pseudocode or the algorithm of quicksort, it mainly contains of two functions. One is the quicksort function, another one is a partition function. In quicksort function, it is a recursive function which divides the array into multiple subarrays until each subarray has either no element or a single element. In partition function, we first select a pivot element, which is the array at the low index. Then we choose I, which is nothing but the low position plus one, and we keep on incrementing I until we find a element greater than pivot. And we also keep on decrementing j, which is pointing at the nth position of the array, and we keep on decrementing it until we find the element lesser than the pivot. We further understand the problem with a small tracing. The main agenda or the main scheme to follow for tracing is that pivot will be the first element or array at the low index. Then we start with I, which is low plus 1, and we keep on incrementing I until we find an element greater than the pivot, and j, which is the nth position, and we keep decrementing it until we find the element smaller than pivot. And if the I is less than j, that is, if index I is less than j, we swap the array at ith index and array at the jth index. And if I is greater than j, we swap the pivot. I will further continue the swapping. Now I is currently at fourth index, and we'll check whether I at fourth index is greater than 8 or not. So 2 is not greater than 8. So we'll increment I to fifth index. So I becomes 5. And since 10 is not less than 8, we'll decrement j to 4. Now it satisfies the criteria that I has an element which is greater than pivot and j has an element smaller than pivot. So now since I is greater than j, that is 5 is greater than 4, will swap array at j and the pivot, that is 2 and 8 will get swapped, resulting the array as 2, 4, 7, 3, 8, and 10. Now, since the array is swapped at index 4, all the elements towards right becomes one subarray and all the elements towards left becomes another subarray. Now, since element towards the right has only one element, so the subarray has only one element, so we don't have to solve it. And since the subarray towards the left has four elements, we need to solve that subarray. So we'll continue by taking the subarray of 2, 4, 7, and 3. So we'll pass this subarray into the quicksort function with lower value as 0 and high value as 3. And in this case, pivot will be 2. Pivot will be 2. I value will be 4. I will be pointing at 4, which is at 1, and J will be pointing at element 3 and also at index 3, 7 and 3. Now, first we'll check whether the element at index 1 satisfies the condition. So, at index 1, we have 4, which satisfies the condition of 4 greater than 2. Then for J, we'll check whether the element is smaller than the pivot, which is 3, which is not smaller than pivot. So, we'll decrement it to uh, 2. Now at array at 2 we have 7. Now 7 is again greater than 2, so we'll decrement it to 1. An array at 1 we have 4. Now 4 is again greater than 2, so we'll decrement array at 0. That is index of j is 0. Now since I is greater than j, that is 1 is greater than 0, we swap array at j and pivot. So in this case, the array remains same, that is 2, 4, 7, and 3, but the pivot value changes. That is, pivot becomes 4 now. Now, as we said earlier, now since pivot value is 4, all the elements towards left is one subarray and all the elements towards right is another subarray. Now, since element toward left is only one, that is subarray has only one element, we don't have to solve it. The element towards right has two elements, so subarray consists of two elements. We need to solve this part of the array consisting of 4, 7, and 3. So we pass 4, 7, and 3 into another same quicksort function with pivot 4, I at index 2 and j at index 3. We keep now first we check whether I at index 2 satisfies the condition which has element 7. So 7 is greater than 4, which satisfies the condition of 7 greater than pivot. So we stop I at 7th index. We do not increment it further. Now j is at 3. 3 is less than 4. So we stop j at third index, and since I is less than j, that is 2 is less than 3, we swap array at I and array at j, that is array at position 2 and array at position 3. After swapping the array, we are left with the array of 2, 4, 3, 7, 8, and 10. Now as we can see, the array is almost sorted. We need to just swap 4 and 3, which we'll be doing in the next step. Now, initially array I was at position 2. Now, when we increment I to third position, we find 7. Now, since 7 is greater than 4 pivot, we stop there. And we decrement j to second position. And since array at second position is 3, which is less than 4, which also satisfies the condition of it being smaller than pivot. Now, since I is greater than j, that is 3 is greater than 2, we swap array at j with the pivot value. That is, array at j, which is 3, will get swapped with 4. So we'll be left with the array of 2, 3, 4, 7, 8, and 10, which is our final answer in the sorted array. So a quick and final summary of our quicksort is: first we choose a pivot at the first element, set I, which is low plus 1, and j is currently high, which is nothing but the size of the array. Then we move I until we find array at ith position greater than pivot, and we move j, that is decrement j, until we find the element that is smaller than pivot. Now if I is less than j, that is index I is less than index j, we swap array at I and array at j. But if array index I is greater than index j, we swap the pivot and array of j. We do this recursively until we have the sorted array.